The contour lines on topographic maps like this one indicate slope and elevation. In this 5-part video series, we'll explore the tools and methods used to determine elevation. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
A mapping survey collects the information we need to make maps. Maps can be enormously valuable for decision making. For example, in modern agriculture, we can use maps to analyze the shape of the land surface and to plan drain tile systems like you see here. We pay close attention to surface slope to produce efficient, reliable systems. You learned that slope is a ratio of rise over run. Rise is a change in elevation, that is a vertical distance, and run is a horizontal distance. Measuring horizontal distance is simple with a tape or with a measuring wheel. But how can we measure the vertical distance, that is, the rise between the points shown here? Well, that vertical distance is best found by a process we call leveling. To most people, this is a level. More specifically, this is a carpenter level. It has a bubble tube that indicates which end of the level is higher than the other. Well, how does it do that? You see, the bubble moves in a curved tube like you see here. That's a very flat curvature. As the tube tilts, the buoyant bubble rises to the highest possible position within the tube. Now, if I can hold the carpenter level steady with the bubble centered within the marks, both ends of the level will have the same elevation. Here you can see that the concrete surface at this end is higher than the concrete surface at the other end of the level. The underside of the level is now a reference line we can use. With the bubble centered within the marks, I can measure down from the underside of the level to the concrete. This measurement is 0.18 feet. Since the other end of the level sits on the concrete, the vertical distance between the two ends is 0.18 feet. By repeating this process over and over, adding measurements end to end, we can find the vertical distance between two distant points. But that becomes very impractical as the horizontal distance increases. So, instead, for leveling surveys, we use instruments like these. This is an optical level. It's basically a telescope that can be oriented to create a horizontal or level line of sight. Well, how does that work? The level telescope contains a crosshair. The horizontal crosshair defines a level plane in all directions. That is, your line of sight through the horizontal crosshair is a level line, perpendicular to gravity. Just like the underside of the carpenter level was held level just a few moments ago, now your line of sight is level. Because the optical level is telescopic, you can see farther. If you can see farther, then the distance between your measured locations can grow. To measure elevation difference with an optical level, we also need a level rod. This one is graduated in decimal feet upward from 0 at the bottom. The difference in two rod readings taken from the same instrument location equals the elevation difference.
Now here are some examples of optical levels. This dumpy level was made around 1915. Notice how long the telescope is. Using the 4 adjusting screws in the instrument base, a surveyor would level the instrument in 2 directions, centering the bubble in its cylindrical tube.
The tilting level represented the next generation of leveling precision. This one was manufactured in the 1940s. As optical science had improved, it sported a shorter telescope and it had an innovative feature that allowed more precise leveling, the split bubble. Below the long bubble tube, an adjustable mirror reflects light into the fluid and bubble in the cylindrical tube. Using a separate eyepiece and another internal mirror, the operator views two halves of the bubble image and adjusts the level carefully to align the two images. Introduced in the 1950s, the automatic level contains a set of tiny mirrors that move automatically in response to Earth gravity, ensuring that the instrument line of sight is perfectly level. If the instrument settles during use, this automatic compensator simultaneously adjusts the line of sight back to the horizontal plane. Here you can see the top of the mechanism moving as the instrument is tilted. Because they contain compensators, automatic levels can give greater precision than older uncompensated instruments can. With the advent of inexpensive laser devices, the rotary laser level has made some leveling surveys possible with only a single surveyor. A revolving mirror produces a horizontal plane of laser light. A laser detector on a special leveling rod enables measurement at each desired location. Farm drain tile installation equipment commonly uses a laser plane to control the pipe depth, ensuring proper slopes and efficient drainage. For high precision, digital levels with advanced internal compensators read the barcode on a special rod while simultaneously collecting atmospheric pressure and temperature readings. Each of these methods creates a horizontal or level line. Using this line, just like we used the underside of the carpenter level, we can find elevation differences, but with a telescope or with a focused beam of laser light, we can extend that line much farther with greater precision.
So far, you've seen the main tools we use for leveling. In the next video, we'll explore the basic processes of a leveling survey. I'm Todd Horton for the Illinois Professional Land Surveyors Association. Equipped with a leveling rod and an instrument, we can measure elevation differences. In this video, we'll explore the basic field processes involved in measuring those differences and then computing elevations. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
Using an optical level, we create a horizontal line of sight. Where our line of sight intersects the level rod, we take rod readings. With these rod readings, we can compute elevation differences. With practice, most instrument operators can confidently read the rod when it is 250 feet away. Thus, if I need to find the rise between two locations 500 feet apart, I simply set up halfway between the points and take two readings. But what if I can't see between those points? For instance, in this scenario, the elevation difference is greater than the height of my tripod. Or what if the locations are 5,000 feet apart? Well, to overcome these obstacles, we perform a level circuit. We perform a level circuit by measuring a series of elevation differences end to end. In the first video, we illustrated the concept with the carpenter level, but now we do the same process on a grander scale with an optical level. To find an unknown elevation shown here on the right, we must first start from an elevation that is known, shown here on the left. An elevation is a vertical distance above or below a reference surface. We commonly use mean sea level as a reference surface. For instance, the summit of Mount Everest is 29,029 feet above mean sea level, and the lowest point in the United States is Death Valley at 282 feet below sea level. By measuring vast networks of level circuits across the continent, surveyors have established heights above sea level at stable, permanent benchmarks. Benchmarks come in many forms and are attached to everyday objects like bridges and fire hydrants. Let's walk through a typical level circuit we call benchmark leveling. You may hear this process called differential leveling or control leveling as well. Here, our survey site is 1/2 mile from the nearest benchmark across a shallow valley. We need to determine the elevation of a newly constructed benchmark on the site. Because of the terrain and the distance involved, we'll have to set up the instrument multiple times to measure a series of elevation differences. First, we'll set up our instrument where we can see the rod sitting atop the known benchmark. Our first rod reading is 4.69 feet. Since this reading is taken on a point of known elevation, we call it a backsite, commonly abbreviated as BS. With this first backsite reading and the known elevation of the benchmark, in our case 842.17 feet, we can say the instrument line of height is 4.69 feet above the elevation of 842.17. Thus, the HI of the instrument, commonly abbreviated as HI, is 842.17 feet plus 4.69 feet, which equals 848.86 feet. When the backsite reading is complete, the rod person can move beyond the instrument operator toward the survey site. At a convenient location where the instrument is visible, the rod person will create a turning point. A turning point is a temporary intermediate point in a level circuit that we use like a benchmark. Each turning point must be stable and have a distinct peak or high point on which the rod will rest. Here, the rod person is using a cold chisel driven firmly in the ground. When it is stable, its top can have only one elevation. This concrete curb has high spots that make good turning points. And this sidewalk corner will work too. With the rod person holding the level rod atop turning point 1, labeled here as TP1, the instrument operator can make another rod reading called a foresight, commonly abbreviated as FS. A foresight is a rod reading taken on a point of unknown elevation. We don't yet know the elevation of turning point 1, so the first reading there is a foresight. Our foresight reading at turning point 1 is 6.08 feet. Since we know the HI is 848.86 feet, and since the instrument line of sight is 6.08 feet above turning point 1, we can now compute the elevation there. We'll subtract the foresight reading from the height of instrument. 848.86 feet minus 6.08 feet equals 840.78 feet. Now we know the elevation of turning point 1. Next, in order to extend our circuit toward the new benchmark, the rod person will stay put while the instrument operator moves beyond turning point 1. At a new location where the rod is clearly visible, the instrument operator will set up the instrument and take a new reading on the rod at turning point 1. Now, here's an important question. Will this reading be a backsite or will it be a foresight? Remember, a backsite reading is a reading on a point of known elevation, and a foresight is a reading on a point of unknown elevation. So, which is it in this case? Well, turning point 1 has a known elevation based on our first instrument setup. So with a backsight reading of 2.95 feet, the instrument has a new HI. That is, the line of sight is 2.95 feet above the turning point 1 elevation of 840.78 feet, giving an HI of 843.73 feet. Now, the rod person can leave turning point 1. Turning points are for short-term temporary use. After reading both a foresight and a backsight on his cold chisel turning point, he can remove it and move beyond the instrument to set a turning point at a convenient location. With a foresight of 7.17 feet, the elevation on turning point 2 will be 836.56 feet. Well, what should happen next? Simple. The process repeats. At each new instrument setup, there will be a new backsight reading and the new HI. At each new instrument setup, the operator will take 2 readings, a backsight and a foresight. At each turning point, the rod person will hold the rod on the point for 2 readings, first a foresight and second a backsight. In the field, the rod person and the instrument operator move separately, taking turns and moving forward in a leapfrog pattern. With the final foresight, there are finally enough measurements with which to compute the elevation of the new benchmark. The process is fairly simple, repetitive, and efficient.
So far, you've seen the core concepts. In the next video, I'll show you how to prevent mistakes, how to record your readings, and how to compute with confidence. I'm Todd Horton for the Illinois Professional Land Surveyors Association. Measuring is only one part of the process in leveling. Equally important are preventing mistakes, recording the readings, and computing results with confidence. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
In the previous video, you saw the basic pattern of measurements we use to find the elevation differences between points on the ground. Our survey started there on the left and ended over here on the right. However, this survey contains no checks. That is, if one measurement is wrong, then the whole survey will be wrong, and we won't even know that it's wrong. Well, perhaps you've heard the phrase, measure twice, cut once. It's a rule of thumb designed to prevent measurement blunders. Applied to leveling, it means that I'll measure the elevation difference proceeding from left to right, and measure it again by proceeding from right to left. Those 2 elevation differences should match very closely. If there's a large mismatch, then there's a blunder in my measurements. The forward run in my benchmark circuit produced an elevation difference of positive 2.79 feet. Well, that value is positive because the new benchmark elevation on the right is higher than the starting elevation you see over here on the left. By contrast, the reverse run yielded an elevation difference of negative 2.81 feet. It makes sense that this value is negative since the reverse run starts higher and ends lower. So the absolute value of these results differs by only 0.02 feet. That's a fairly small error for a survey of this type. Now, why don't these 2 values match exactly? Because there is error in every measurement. As it applies to measurement, the term error does not mean mistake. A mistake really is a blunder. For instance, simply misreading the level rod is a blunder. However, the term error describes the natural random variation in repeated measurement results. if you measure something multiple times, it won't come out exactly the same every time. If you round your reading to the nearest 1/100th of a foot, that rounding is literally an error source. Sometimes you round up, sometimes you round down. If the level rod is not completely vertical at the time of reading, there will be a small error in the measurement. These and other error sources will largely, but not completely, cancel each other out. The remaining error at the end of our level circuit is called closure error. Now, to compute closure error, we're going to subtract the known elevation from the calculated elevation at the benchmark where the level circuit ends, where you can see over here on the left. Starting with the forward run and returning to the known benchmark on the reverse run, we calculated the ending elevation to be 842.15 feet. However, that benchmark already had a known elevation of 842.17 feet that you can see in parentheses at the left. Therefore, 842.15 feet minus 842.17 feet equals a negative 0.02 feet. That is, the level circuit closure error is negative 0.02 feet. For leveling, there is a standard format for field notes that tells the trained reader not only the measurements, but also the sequence of the measurement. The terms from the previous video, that is backsight, height of instrument, and foresight, form the structure in good field notes. Every measurement in our level circuit needs location information in order to be meaningful. The left column in the leveling notes is reserved for measurement location. In some types of surveying, the location is called a station. Well, here you can see the word station has been abbreviated to the letters STA. The next three columns will contain backsight readings, abbreviated as BS, heights of instrument, HI, and foresight readings, FS. The fifth column will contain elevations. Well, first, we'll set up our instrument where we can see the rod sitting atop the known benchmark. In the notes, we'll record the rod location, in this case, BM for benchmark, in the station column. Since the benchmark elevation is known, we'll record that in the elevation column. Our first rod reading is 4.69 feet. Since this reading is taken on a point of known elevation, we call it a backsight. Since the backsight reading was taken with a rod atop the benchmark, we'll record 4.69 feet in the backsight column on the benchmark row. Armed with this information, we now have sufficient data to compute the height of instrument. Since the line of sight is above the point where the rod sits, we'll add the backsight reading to the elevation. At this instrument setup, 4.69 plus 842.17 equals 848.86 feet. We'll record that result in the HI column in the next row down the page. When the backsight reading has been recorded, the rod person moves beyond the instrument operator to create a turning point. We'll start a new line below the one containing our first HI, labeling it TP1 for turning point 1. With the rod atop the first turning point, the instrument operator reads 6.08 feet for the first foresight. In the new TP1 line, we'll record 6.08 in the foresight column. Turning point 1 is physically below the instrument line of sight, which has an elevation we call the height of instrument. For this setup, the HI, as we said a moment ago, is 848.86 feet. Therefore, 848.86 feet minus 6.08 feet, the foresight reading, equals 840.78 feet. This is the elevation of turning point 1, and we'll record that in the elevation column on the turning point 1 line. Now that turning point 1 has a known elevation, the instrument operator will pick up the instrument move beyond the turning point and set up again. The first reading, as we call it, the first shot, is a backsite to turning point 1. Notice here that we'll record that reading in the backsite column on the turning point 1 line. With that information, we compute a new HI. Next, the rod person moves forward, sets a new turning point, TP2. After reading and recording the foresight on turning point 2, we now have enough information to compute the elevation at TP2. Have you seen a pattern in the field notes so far? The readings and the math follow a repeating sequence back and forth down the page. Plus, the location of any number within the grid identifies that number. For instance, we know that this reading was a backsite on turning point 1. Why? Because it is in the backsite column on the turning point 1 row. This HI corresponds to the setup between the benchmark and turning point 1. As the level circuit progresses, the field process and note keeping advance in this pattern. The backsite comes first, the rod person moves forward and sets a turning point. Then comes the foresight. After the foresight, the rod person stays put while the instrument operator moves forward, resets the instrument, and repeats the process. In this type of level circuit, there will always be one backsite and one foresight for each setup. The number of HIs in the notes tells us the number of setups in the survey. At the end of the forward run to our new benchmark, we have effectively measured once. That is, we measured the elevation difference between the known benchmark and the new benchmark going forward. But we haven't yet proven that our measurements are reliable. Therefore, we'll measure the same elevation difference again, but now in the opposite direction. So far in this video, you've seen the computation for HIs and elevations appearing conveniently with the readings. In real life, it's best to simply record the readings in the field without computing the HIs and elevations as you go. Then, when all the measurements are done, sit down and do all the math at once. You'll make fewer mistakes when you follow this rule of thumb. Here's how the process will look. On our reverse run, we'll simply record backsites and foresights, saving the computations for later. With the instrument in a new location, we'll take a backsite on the new benchmark, recording it in the appropriate row in the backsite column. Then, going back to turning point 4, we'll take a foresight reading there. Without computing the HI or elevation, we'll move forward. Notice that just as before, our field note entries alternate back and forth as you move down the page. Now, with the forward and reverse runs complete, we say that we have closed the level circuit. This circuit started and ended at the same point. It closed where it began. So now let's finish the circuit computations. For the forward run, we already calculated the new benchmark elevation. So let's add the next backsite reading to that elevation to get the HI between the new benchmark and turning point 4. Next, we'll subtract the next foresight on turning point 4 to find the elevation on turning point 4 again. Now notice that our notes continue in the upper right corner of the screen here. Notice that below the new TP4 elevation is another number in parentheses. The parentheses around this number indicate that this is a previously determined value. In fact, it is the value we computed from the forward run of the circuit. This shows us then that we have small errors accumulating in our readings. This is a natural consequence of things like rounding our rod readings to the 100th of a foot. This type of check helps us find rod reading errors and math errors. So be sure to compare the elevations from your forward and reverse runs. The computation process continues until we reach the end of the circuit. Here you can see that the two final elevations, that is, original and computed, for the known benchmark differ by 0.02 feet, or 2/100ths of a foot. This is the closure error in the circuit. Well, these numbers look good so far, but we haven't yet proven them to be reliable. We now need to check our arithmetic. It's very easy to blunder simple math, so we'll perform an independent arithmetic check. First, sum up all the foresight readings. In our case, they sum up to 56.99 feet. Then, sum up all the backsight readings. Here, they sum up to 57.01 feet. To complete the arithmetic check, we have a simple sequence. To the starting elevation, that is the elevation of our known benchmark, let's add the backsight sum and subtract the foresight sum. This result should match the ending elevation you computed in the tabular field notes. If these numbers don't match, then there is a computation blunder somewhere in the process. When that happens, carefully recompute your work until you find and correct the mistake.
Equipped with these methods for preventing mistakes and checking your work, you're ready to move forward into more common level circuits. In the next video, we'll explore how to use profile level circuits for mapping surveys. I'm Todd Horton for the Illinois Professional Land Surveyors Association. The leveling process measures elevations for mapping and for solving problems. In this video, we'll use another leveling method to begin designing a waterway improvement. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
In the last video, you saw the field process and note keeping for a benchmark leveling circuit. Also called a differential leveling circuit, this survey used multiple instrument setups, and at each setup, the surveyor measured one backsight and one foresight. In keeping with the adage, measure twice, cut once, the level circuit had a forward run and a reverse run. Because this level circuit ended where it began, we call it a closed loop circuit. Since there was only one known benchmark available, all the elevations in the survey are measured relative to that one benchmark. Let's suppose two known benchmarks are available near your project site. You plan to create a new benchmark, but which known benchmark should you use for your survey? Benchmark A or benchmark B? If benchmarks A and B were created in the same original survey, then you can use both. Start the level circuit on A and end the circuit on B. We call this a closed link circuit. That is, your new level circuit links between two known benchmarks. Link and loop level circuits both begin and end on known benchmarks. Ending on a known benchmark makes the level circuit closed. At the closing benchmark, you can compute the closure error in the circuit. If there are closed circuits, then it's possible to have an open circuit. In surveying, an open level circuit does not end on a known benchmark, so it contains no check for blunders and errors. For instance, if we skipped the reverse run of the closed loop circuit from before, it would instead become an open circuit. Because an open level circuit does not self-check like a closed circuit, you should always use closed level circuits.
So far in this video series, we've explored benchmark leveling. It's a great place to begin learning, but there is a more common leveling method we use to solve all kinds of problems.
Imagine that your farm has a grass waterway like this one. When properly constructed, this waterway reduces erosion, prevents ponding, and allows easy travel by vehicles and machinery. The waterway profile, that is, the changing slope along its path, must harmonize these goals. However, your waterway has a ponding problem. So how do we begin to solve this problem? We can use a method called profile leveling. The idea is to measure the elevation at intervals along the waterway profile. Equipped with this information, we can design a new waterway profile and excavate the soil that caused the ponding problem. Here's a simplified map of your waterway. Computing waterway slope requires not only elevation difference, but also horizontal distance. For simplicity, we use a system called stationing to indicate horizontal distance. Very similar to mile markers along a highway, stations tell us the distance from an origin point. We'll mark the low end of the waterway with a wood stake labeled with station 0 plus 00. The plus sign in this station is a placeholder between the tens and 100s places. The plus sign identifies this number as a location, just like the highway mile marker. By measuring along the waterway center line, we can mark a new station every 100 feet. Remember, the plus sign in this station is a placeholder between the tens and 100s places. So when we've measured 100 feet from the 0 plus 00 origin, we can mark that as station 1 plus 00. Station 2 plus 00 is 200 feet from the origin. Station 3 plus 00 is 300 feet from the origin. This system allows more specific locations as well. The deepest ponding in your waterway occurs at station 6 plus 72. Station 6 plus 72 is 672 feet from the 0 plus 00 origin. Now that we have the stations marked, it's time to use profile leveling to measure the elevation at those stations in the waterway. We'll set up our instrument where we can see the starting benchmark and several of the station marks. Our first rod reading is a backsight on the benchmark, and our first foresight will be at station 0 plus 00. Instead of moving the instrument like in benchmark leveling, we can continue reading the rod at the next station marks. When distance or obstacles prevent us from taking more readings, then we'll establish a turning point and measure a foresight there. Remember that in benchmark leveling, for every instrument setup, there is one backsight reading and one foresight reading. However, in profile leveling, for every instrument setup, there is still only one backsight reading, but there can be several foresight readings, as you see here. This is the primary difference between benchmark leveling and profile leveling. After reading the foresight at the turning point, we'll move the instrument where we can see the turning point and the remaining station marks. With a backsight reading taken at the turning point, we're ready to read foresights on the waterway stations. There is another benchmark nearby, so we'll close our level circuit there with a final foresight reading. Since we didn't return to the starting benchmark, this is now a closed link circuit. That's how the process will look. Let's wade deeper into the water and explore proper note keeping and computations for profile leveling. Just as before, our notes will have the standard 5 column headings for station, backsight, height of instrument, foresight, and elevation. Benchmark A has a known elevation of 585.95 feet recorded in the elevation column in a new row labeled Benchmark A. The backsight reading goes in the backsight column on that same row. It's a good idea for learners to mark a dash in the foresight column now. This can prevent recording a foresight reading in the wrong place. Our first foresight reading belongs in the next row, labeled here as station 0 plus 0, 0. Each new foresight gets its own new row. Now we'll start our computations. Since all 6 of these foresights were read from the same instrument setup, we'll use the same HI value for all 6 elevations. Watch this. By adding the backsight reading to the benchmark elevation, we get the HI of the first setup, 595.28 feet. The HI is the elevation of the instrument line of sight. Subtract the first foresight reading from the HI to get the elevation at station 0 plus 0, 0. Then subtract the next foresight from the same HI for the elevation at 1 plus 0, 0. Repeat this process for all the foresight readings corresponding to that HI. Since the last foresight from the instrument setup is a turning point, we'll read the backsight for the next setup at that same turning point. Since we created the turning point row during the first instrument setup, we'll now record the next backsight in that same row. Once again, we'll add the backsight reading to the turning point elevation, and we get the HI of the second setup, 601.24 feet. From this new HI, we'll measure the foresights to station 6 plus 0, 0 through 10 plus 0, 0. Since the second setup has a new HI, we'll use that HI to compute all the foresight elevations according to this setup. Now, the final closing rod reading is on our ending benchmark. It may be tempting to call this a backsight, but actually, it's a foresight. Remember that there is only one backsight per instrument setup. For this setup, we took the backsight reading at the turning point. Therefore, the rod reading on the ending benchmark is a foresight. Benchmark B had a known elevation prior to our survey. It is common practice to show the known elevation of the ending benchmark in parentheses adjacent to the measured elevation. As we discussed in an earlier video, the difference between these values is our circuit closure error. This is a good time to illustrate an important note-keeping pattern. Notice that the foresight on turning point 1 was taken from the first setup. Therefore, the elevation of turning point 1 is computed from the first HI. The row for turning point 1 also contains the backsight and HI for the second setup. And the elevation of the closing foresight is computed from the final HI in the circuit. The arithmetic check for profile leveling requires careful attention. First, let's review the arithmetic check for the benchmark leveling circuit in the previous video. That circuit had 10 setups. How can we tell that from the notes? Well, simply by counting the number of HIs. Remember, there is only one HI per setup. Since there is only one backsight per HI, then there are 10 backsight readings. And since a benchmark circuit has only one foresight per setup, then there are 10 foresight readings. For our arithmetic check, the number of backsight readings and the number of foresight readings must be equal. So now for profile leveling, the same pattern applies. In our profile leveling circuit, we had 2 setups and thus 2 backsight readings. Here, the sum of the backsights is 16.95 feet. Now we need to sum 2 foresights. But which two foresights must we choose? If we add up all 13 of them, that total just won't be reasonable. So here's the rule for selecting the correct foresights. Use only those foresight readings taken at turning points and at benchmarks. The foresights taken on the profile stations do not affect the closure of the circuit. Thus, applying this rule, the sum of foresights on our turning point and benchmark is 5.23 feet. Here you can see that our arithmetic check confirms that the closing elevation in the field notes is correct. If these two results don't match, then there is an arithmetic blunder that must be found and corrected. So now, armed with measured elevations in your waterway, we can design a new waterway profile and excavate the soil that caused your ponding problem. Profile leveling makes the solution possible.
Now that you've seen the fundamentals of leveling, it's time to explore quality control. In the next video, we'll look at quality standards, error management, and instrument calibration. I'm Todd Horton for the Illinois Professional Land Surveyors Association. The quality of our measurements can vary considerably, so the amount of acceptable error depends on the intended use of the measurement. In this video, we'll explore instrument calibration, error management, and quality standards. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
Every optical surveying instrument requires periodic calibration. Internal wear and tear caused by normal use and handling can slowly degrade instrument accuracy. Calibration includes carefully analyzing the instrument's accuracy and, if needed, adjusting it to restore degraded accuracy. Complex instruments like this total station may require calibration by a trained specialist. Common automatic levels can be calibrated by an experienced user. Collimation is the technical term for the adjusting of the line of sight in an optical device. To test this collimation of an automatic level, we commonly perform a peg test. The peg test is designed to determine whether the instrument line of sight is truly horizontal. If the level is out of calibration, then the line of sight can have either an upward or a downward slope leading to rod reading errors. To begin a peg test, we mark two stable points 200 to 300 feet apart and set up the instrument at the midpoint between them. In this configuration, we say that the backsight and foresight distances are balanced or equal. First, carefully read both rods and record readings R1 and R2. Because the distances are balanced and because the slope in the line of sight is identical for both readings, the error in reading R1 is equal to the error in R2. Therefore, these two errors, E1 and E2, cancel each other, and the true elevation difference is simply the difference in the two rod readings. For our example here, reading R1 is 5.43 feet, and reading R2 is 3.21 feet. So the true elevation difference is 2.22 feet. Next, we'll move the instrument to within 5 feet of one of the rods, making our sight distances highly imbalanced. Here we'll take readings R3 and R4, and once again the slope in the line of sight is identical for both readings. But now notice that error 3 and error 4 are now very different due to the imbalanced distances. In fact, because the distance to R3 is so short, error E3 rounds off to 0 feet. Here in our example, reading R3 is 4.72 feet and reading R4 is 6.97 feet. Now watch carefully. Reading R3 plus the elevation difference found from the first setup will give us a result called R4 ideal. R4 ideal is the theoretical reading we should get if the line of sight is truly horizontal. However, if the instrument requires adjustment, then R4 ideal will not equal reading R4, as you see here. When we subtract R4 ideal from reading R4, the difference is the vertical error in the instrument line of sight. To minimize this error, we adjust the crosshair of the instrument. Automatic levels typically contain at least one adjusting screw, concealed under a cover, that can raise or lower the crosshair to indicate the correct reading. This is a very tedious and delicate process. Experienced instrument operators can do this in the field. However, most people prefer to have this done by a trained specialist.
Whenever you use an optical level, your first question about that instrument should be, is it properly calibrated? Keep a permanent record of your calibration notes. If the instrument calibration is over 1 year old, it's overdue for another check. Some professionals calibrate their levels monthly to ensure quality measurements.
Use balanced distances to minimize the effects of possible calibration problems. Remember, when the distance to the backsight reading matches the distance to the foresight reading, the errors in each reading cancel each other. This gives the true elevation difference. This is nearly impossible to do in profile leveling, but it is especially desirable and achievable in benchmark leveling. When running a benchmark level circuit, do your best to keep each foresight distance balanced with its corresponding backsight distance. The lengths can change from one setup to the next, but try to keep the distances within each setup roughly the same as you can see here. Instrument calibration addresses the slope or tilt in the line of sight. Another type of tilt can also degrade our measurement accuracy, rod tilt. Our goal is to read the rod when it is truly vertical or plumb. But if it is tilted away from vertical, the line of sight no longer intersects the rod at the minimum distance above the measured point. When tilted, the rod shows a false reading that is numerically higher than the true vertical reading. So how can we ensure the rod is vertical? There are two common methods. First, this small device, often called a rod level, when held against the rod, uses a circular level vial to indicate when the rod is plumb. Second, if you don't have a rod level, you can rock the rod smoothly back and forth in the direction of the instrument. As the rod passes through the vertical position, the instrument operator will see the reading reach its minimum value momentarily. To ensure the rod is vertical relative to the instrument operator's left and right, stand behind the rod looking toward the instrument. Use your peripheral vision to search out visual clues to help you keep the rod plumb, left and right, as you rock it smoothly forward and back. Do your survey partner a favor. Grip the rod by its sides to prevent your fingers from obstructing the readings. These methods are designed to minimize errors, but it is impossible to completely eliminate measurement errors. So, how much error is acceptable? The size of acceptable error depends upon the intended use of the measurement. In previous videos, we indicated the overall accuracy of our level circuits using the circuit closure error. This is the difference between the known elevation and our computed elevation at the ending benchmark. To evaluate the quality of the work, we compare that circuit closure error to the allowable error. The allowable error depends on the horizontal length of the circuit from the starting benchmark through each turning point to the ending benchmark. For example, consider a closed loop circuit that is 3/4 mile long from beginning to end. The allowable error computation has just one input, circuit length. In this case, 3/4 or 0.75 mile. The result is plus or minus 0.043 feet. Since our circuit closure error is less than or equal to this allowable error, our level circuit is acceptable. However, if the closure error were to exceed the allowable error, the closure error would be unacceptable. The remedy then is to remeasure the circuit in part or in whole until the error source is discovered and corrected. This allowable error standard is one of the lower quality standards established by the FGCC, or Federal Geodetic Control Committee. Third order leveling closure, as we have seen here, is adequate for all agricultural and most construction and engineering applications.
To be successful in leveling requires careful error management. All measurements contain error, but by applying solid practices and anticipating a variety of error sources, you can perform leveling surveys with consistent accuracy and confidence. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
I wouldn't call anything a surprise, really. Just excuses.
Everyone agreed that the Earth was flat. Flat. Everyone agreed that the Earth was flat. 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 Flat.
Everyone agreed that the Earth was flat.
Have a great day.